Assalamualaikum and hi, my name is Fasihah binti Lukman Hakim and my research title is Smart Biodegradable Packaging Films based on Anthocyanin, Infused, Chitosan and Carboxymethylcellulose (CMC) for monitoring the freshness of meat. The following are my presentation outlines. For introduction, food spoilage is a major global problem leading to excessive waste with serious economic and environmental effects. One of the main causes of spoilage is microbial growth, which can also lead to foodborne illnesses. Traditional methods like sensory checks and microbial testing often fail to detect early signs of spoilage. To address this, smart packaging has emerged. Intelligent packaging uses sensors to monitor food quality in real time. This helps reduce food waste, prevent illness, and make expiration dates more accurate. However, these systems can be expensive and face challenges like regulation and sensor interference. Recently, biodegradable smart packaging has gained attention. Materials like chitosan and carboxymethylcellulose or CMC are great options. They are biodegradable, safe, and have good film forming properties. Anthocyanins, like those butterfly pea flower, are natural pH indicators. They change color as pH levels shift, make them perfect for detecting spoilage in meat. As the meat spoils and pH rises, the film changes color, offering a clear visual indicator. These natural sensors are eco-friendly and effective for freshness monitoring. Previous research on smart biodegradable packaging hasn't fully explored the combination of anthocyanin from butterfly pea flower with chitosan and CMC polymers. In particular, there's a gap in studying how this mix affects the film's mechanical and physical properties, as well as how the film changes color when in contact with chicken meat during storage. This study is important because it looks at how strong and flexible the film is, key factors for making reliable packaging. It also examines how well the film can protect food and signal spoilage through visible color changes. These features are especially relevant today as the food industry looks for smarter, more sustainable packaging that can extend shelf life and give clear signs of freshness to consumers. This study has two main objectives. First, to investigate the mechanical and physical properties of a pH-sensitive film made by combining anthocyanin from butterfly pea flower with chitosan and CMC. Second, to observe the color changes of the film when it is exposed to chicken meat during both cold and room temperature storage. For my literature review contents, first, anthocyanin are natural pigments found in many fruits and vegetables. They belong to polyphenol group and are known for their ability to change color depending on the pH level. This unique property makes them highly useful in intelligent packaging, especially for monitoring food freshness, since anthocyanins are stable at room temperature and can detect early signs of microbial growth and spoilage. They help ensure food safety. Next, research also has looked at how anthocyanins interact with polymers. For example, when anthocyanin is added to a chitosan matrix, the film's pH sensitivity improves and becomes more responsive. Biodegradable polymers like cellulose and carboxymethylcellulose or CMC are often used because they provide good mechanical strength and are cost-effective. This combination results in color-changing films that can serve as smart pH sensors to track food freshness. Several factors influence the performance of smart films used in pH indicator packaging. A variety of water-based polymer can be used, such as PVA, starch, and chitosan. For effective performance, these polymers must be colorless, moisture-sensitive, stable at low pH, and have good mechanical strength. In many cases, combining different polymers improves their properties. For example, using extracts like blueberry, red cabbage, or blackberry along with polymers can enhance the sensitivity and stability of the film. The choice of polymer plays a big role in how well the film performs. The color changing mechanism is one of the most important features of these films. Anthocyanin-based films from sources like red cabbage, butterfly pea flower, and plum skin show clear visual changes such as the pH level increases during food spoilage. For example, when used with prawn, pork, fish, or chicken, the film changes from pink or purple to green, blue, or grey, depending on the level of spoilage. These changes are a direct result of microbial activity and help indicate food freshness clearly. For the methodology, the first one is extraction of anthocyanin from BPF. To extract anthocyanin from butterfly pea flower, we began by preparing 30 grams of BPF powder. The extraction was done using a solver method where the powder was mixed with 240 ml of 50% alcohol. This mixture was stirred for 2 hours at 350 rpm and then left to stand overnight. Next, the solution was filtered and the solvent was reduced using a water bath and heated at 75 degrees Celsius for 2 hours until the volume dropped to 57 ml, which is half of the original volume. Finally, the extract was stored in a tightly sealed container, kept in chiller and covered with aluminium foil to protect it from light. This method follows the procedure outlined by Fernandez Marin et al. And Gasti et al. After extracting anthocyanin from butterfly pea flower, the next step was to prepare the smart films. First, two separate solutions were prepared, one containing Chitosan by dissolving 1 gram of Chitosan in 100 ml of 2% acetic acid and another containing 0.5 grams of CMC in a mix of 30 ml warm and 20 ml cold water. These two polymer solutions were then combined into a 2:1 ratio, 1 gram Chitosan to 0.5 gram CMC, and stirred for 20 minutes at 350 rpm to ensure uniform mixing. Next, anthocyanin extract was added to the mixed solution. For the 5% film, 2.5 ml of extract was added, and for the 10% film, 5 ml was used. The mixture was then poured into 8 cm petri dishes for casting and left to dry completely for 3 days. Once dried, the film were carefully removed using tweezers and stored in a desiccator until further use. The following chart shows my experimental design. Next, for result and discussion, the first one is thickness of film. Thickness is an important factor when evaluating the film strength and transparency. In this study, we found that films with BPF extract were thicker than the control film. This is because adding more anthocyanin increases the total solid content in the film, leading to greater thickness. A similar pattern was also seen in films using mango leaf extract, as reported by Adila et al. 2018. So, as the BPF concentration increases, the film becomes thicker due to changes in the polymer structure and the distribution of natural compounds. This supports the idea that BPF plays a strong role in influencing film properties. Next is transparency. Transparency is an important feature in food packaging, especially when product visibility is needed. In the results, the control film showed the highest transparency at 72.78% and the lowest absorbance of 0.138. As BPF concentration increased, transparency decreased significantly. This is due to the higher anthocyanin content, which creates a denser film structure that blocks more light, while darker films can help protect light-sensitive products. Clearer films are better when consumers need to see the food inside, so the right film composition should be chosen based on the intended function and appearance of the packaging. Other than that, moisture retention capacity or MRC increased with the addition of anthocyanin due to stronger hydrogen bonding. However, at 10% concentration, MRC slightly decreased, likely because of the matrix saturation or pigment aggregation. Water solubility also increased as more BPF was added. This is because the polar groups in the extract interact more easily with water. While high solubility is useful for biodegradable or edible films, it can reduce the film stability in humid conditions, making it less ideal for long-term packaging. Among all samples, the CS and CMC BPF 5% film showed the best balance between moisture retention and solubility, making it the most suitable choice for smart packaging applications. For mechanical properties, the tensile strength of all films remain consistent, ranging from 1.046 to 1.052 MPa. This means that adding BPF didn't weaken the film structure. However, elongation at break, which shows flexibility, was highest in the 5% BPF film at 70.23%. This is more flexible than the control at 61.14% and the 10% BPF film, which dropped to 51.25%. The reduced flexibility at 10% could be due to too much anthocyanin, disrupting the polymer matrix. Overall, the 5% film had the best mechanical performance, strong and flexible, making it the most suitable for smart packaging applications. Next is the BPF anthocyanin solution and film color changes at different pH. The CS-CMC BPF film showed clear and visible color changes when exposed to different pH levels ranging from 1 to 13. At low pH, the films appeared pink to red, shifting to blue around neutral pH and turning green to yellow in alkaline conditions. These changes are due to the structural transformation of anthocyanins, which are naturally pH-sensitive compounds. This result confirmed that the film acts as an effective halochromic indicator, making it highly suitable for smart packaging applications that monitor food freshness. In a spoilage trial using fresh chicken meat, the 5% film showed clear pH-responsive color changes that indicated meat freshness. At room temperature, the meat pH increases from 6.23 to 7.65 after 48 hours, and the film changed from blue to greenish blue. This color shift reflects increased microbial activity and spoilage. In contrast, under cold storage, the pH only slightly increased from 6.1 to 6.32, and no visible color change was observed, indicating that the meat remained fresh. This result matches the non-pH sensitivity of anthocyanins and demonstrates the film effectiveness as a real-time freshness indicator. Overall, this supports the potential use of smart packaging in consumer and retail environments to monitor meat spoilage visually and reliably. In conclusion, a smart film based on butterfly pea flower anthocyanin was successfully developed for monitoring meat freshness. The film's thickness, transparency, moisture retention, and solubility were all influenced by the concentration of BPF extract. Among all samples, the 5% BPF film showed the best performance. It had the highest flexibility, a balanced moisture profile, and strong pH sensitivity, with a clear color shift from reddish purple in acidic conditions to green-yellow in alkaline environments. It also worked effectively as a freshness indicator for chicken meat. Therefore, the CS-CMC BPF 5% film is the most suitable option due to its physical, mechanical, and sensing properties. For future studies, improving water resistance is recommended, possibly by adding cross-linking agents or hydrophobic additives. Also, exploring other natural pH indicators like roselle extract may expand the range of detection and extend shelf life monitoring for different types of food. This is my FYP Gantt chart, and these are all my FYP references for this FYP research. That's all from me. Thank you for watching.